Welcome back, everybody. So today we're going to be talking about definite integrals for a function, as opposed to the indefinite integrals that we were working on earlier. And this may seem for a minute unconnected to the topic of Riemann sums, which we've been doing over the past couple of days, but it'll turn out to be a really magical connection between Riemann sums and integration. So let's begin with a little bit of terminology. We have f of x, a function, and we have capital F of x, which is any antiderivative of f of x. It could be your favorite antiderivative, it could be my favorite antiderivative, doesn't matter at all. If you see notation, like this one here, integral from a to b of f of x dx. This is just like the indefinite integral symbol, except this time there are numbers on the bottom and top of the elongated s. This is called a definite integral, and this is what it's telling you to do. If you see a definite integral, what it wants you to do is not to calculate the antiderivative, not just that, but calculate the antiderivative at the top number b. Calculate the antiderivative at the bottom number a, and then take the difference of those two numbers. Plug in the top number, plug in the bottom number to any antiderivative, and then subtract those two results. That's what this notation is asking you to do. Now we'll see a concrete example of this very soon. But before I go into that, I just want to establish some common terminology. This number a, which appears at the bottom of the elongated s, this is called the lower limit of integration. And similarly, on the top of the elongated s, the number b is called the upper limit of integration. F of x, the function that's being integrated, is called the integrand. Integrand, the function that is being integrated. And in this context, the letter x, this is called, oftentimes called the dummy variable. I think dummy in terms of like a mannequin or a training dummy or something like that. It's not quite alive, and it doesn't really have an impact on the final answer to this question. As you can see, in the final answer of this definite integral, the letter x won't actually show up at all. You will typically have something only involving b and a, which are numbers, or you have a final answer which is just a number. X does not have anything to do with the final answer, typically. And to reinforce that point, we have here an example, an exercise. Calculate the definite integral from 1 to 5 of 3 dx. Let's go about doing that. Now, first things first, what we have got to do is we have got to come up with some antiderivative of 3. So let me just put a little thought bubble here underneath. My favorite antiderivative of 3 is probably 3x. The most general antiderivative would be 3x plus 3 plus c, but my favorite antiderivative would be 3x. So I'm going to take 3x, and I'm going to plug in the upper limit 5. And I'm going to take 3x, and I'm going to plug in the lower limit 1. And then I'm going to subtract these two values. The result of this will be 3 times 4. The result of this would be 12. Now let's have a look at the side here. And let's graph f of x equals 3 on the interval from 1 to 5. Since this function is constant, its graph will be just a straight line at height 3. Now what's interesting is that if we consider the area under this graph, we can actually calculate that area very easily. by taking the height of this rectangle, 3, multiplying it by the width of this rectangle, 4, and the result of that is an area of 12. So that's pretty interesting. The value that we got from this definite integral is precisely the same as the area under the graph of the integrand. Now at this moment, I'm going to introduce some notation that can make it a little bit easier to show your work as you're doing these problems. Instead of jumping straight to antiderivative at b minus antiderivative at a, you will often see this notation used to express that difference. Capital F at x, and then a large, straight, vertical bar. At the bottom of the bar, a, and at the top of the bar, b. This is shorthand for I'm about to plug in b, plug in a, and then take the difference. Let's use that notation here in our second example. Calculate the definite integral from 0 to 4 of x times dx and compare the result to the area under the graph. So let's once again consider what is your favorite antiderivative of x. My personal favorite antiderivative of x is the simplest one, x squared over 2. And I'm going to use this straight vertical line from 0 to 4 to communicate that in my very next step, I'm going to plug in 4, I'm going to plug in 0, and then I'm going to take the difference of those two numbers. The result of this being 8. Now let's do a graph on the side to see about the area under this graph. So here is f of x equals x, identity function, from x equals 0 to x equals 4. And the region under that graph is a triangle. So the area can be found by taking 1/2 base times height. And that's 16 divided by 2. And so once again, we have gotten back exactly the value of the definite integral. And so what we're going to do in the next video is introduce a theorem given the grand and well-earned name of the fundamental theorem of calculus, which makes this relationship concrete.